Prabha. Digital India. Educated India.
Now let us imagine that below the surface of water we have a plate which is kept something like this. Let us try to rationalize the force acting on this plate on one particular face, on the left face for example. Let me call this A and let me call this as B. So we know that pressure at A is less than the pressure at point B, and the pressure, it increases linearly. So it may look something like this. So the force is biased towards point B. So if this is the centroid of AB, then a larger amount of force is distributed on the lower part of this centroid than the higher part of the centroid. So in that case, we can sort of imagine that the neutral axis, or the point where the effective force is set to act, can lie somewhere over here. It is not going to be at the centroid. When can the force be acting at the centroid? When the pressure is uniform. If this is the kind of pressure distribution by whatever means, then yes, we can say that the net pressure acts through this point. So with this physical intuition in mind, let us proceed to quantify the facts stated before. So at a given point, say at a distance z from the surface, the force acting on a differential element, say the area is dA, will be equal to it will be simply P times dA. It is the differential force, and hence the integration will not exist. And P is rho g z, and the dA appears as it is. So then we can find out the total force acting on the object as integral rho g z dA. And depending on how A varies, it need not be a two-dimensional object. But if it is a two-dimensional object, say the cross-section, the side view is this, but the isometric view is something like this, then the area does not sort of vary with z. The area is simply equal to,
let us see how we can define this. If this is the side view of the plate, that is AB, then the front view of AB, if it is something like this, let's say it's a rectangular plate, and if this is the distance z, then this thickness, this area, that is this projected area, will be equal to the breadth of the object multiplied by dz. So this will be integral rho g z times dz times the width, and so it is rho g w integral z dz. Essentially it is rho g w z square upon 2, where z varies from za to zb. So this gives us an idea on how to find the force, and clearly the force is not going to act through the centroid, and in fact in what follows we will find out how to find a general way of finding out what is called as the center of pressure. But let's proceed for now. Let us consider the more general case where there is a free surface and there is a flat object immersed into the surface, so that the side view is flat and the side view makes an angle theta with the free surface.
now the direction of the force will be orthogonal to the shape of the plate. While we have only drawn the side view, there is no constraint on how the front view will look. The front view will be orthogonal we will look at this object from here that is orthogonal to the area, and let us draw an arbitrary shape, because it will not really matter how the shape will look like. So something like this. Okay, so let's say this is the shape. Let's say we focus our attention at a certain distance, at a certain depth h from the free surface of the water, and let us draw from the centroid. So this is the centroid of the object, or maybe it's a bit lower than what I've shown. Maybe this is the centroid of the object. Let us call it C. Let us draw the x and the y axis. So let this be y and let this be x. So if we map it to this, then this direction will be y and x is coming out of the plane. Now at a given depth h from the free surface, if we project h onto the object, this is the red line is the area along which the force will act. The pressure times this area will be the force. So the force is equal to integral P dA, and the pressure at this particular point, so it will be equal to the atmospheric pressure plus rho g h. So this can be simplified as P atmosphere plus rho g h times dA. Now the first integral is quite simple, so it is PA dA plus integral rho g h dA. The first integral, because PA is constant, so it is PA times A, while we have to do something about the second integral. But rho into g is constant, as we have previously seen that rho and g do not vary much and they can be assumed to be constant with depth. So it is rho g integral h dA. Now let us cast h in terms of the slant coordinate, that is the coordinate oriented opposite to y, but they are collinear, but it originates at the point where the axis of the object meets the free surface. So let's call this variable as xi. So from trigonometry we know that xi sine theta is equal to h. That is the xi coordinate of this particular point. If I call this point as A, so the xi coordinate of A is equal to h upon sine theta. So we can, let us simplify this. So PA times A plus integral rho g. Now h is xi sine theta, so this becomes xi sine theta dA. Now because sine theta is constant, it is PA plus rho g sine theta integral xi dA, and integral xi dA is nothing but it is tantamount to finding out the location of the centroid of the object, this point, with respect to this particular point at the free surface. Okay, this is going to be equal to xi center of gravity times the area of the object, and this is by the very definition of the centroid of the area, and hence this is going to be PA times A plus rho g sine theta times xi centroid times A. But sine theta times xi centroid is also equal to the depth of the centroid. That is, if I can use this equation to write xi centroid sine theta is equal to h centroid. So if this is the centroid, this particular distance from the free surface, let's call this O. So OC is equal to xi centroid, and if I call this as C, not C because we have used it, let me call it B. So B, rather, if this is the centroid, let me extend it to this point. So if this is C prime and if this is B prime, so BC prime, that is the depth of the centroid from the free surface. So B prime C prime is equal to H of the centroid, and thus this expression becomes PA times A plus rho G H centroid times A, because xi c sin theta is H centroid, and effectively this is PA plus rho G H C times A, that is the pressure acting at the centroid of the object times A. Interestingly, the force acting on this particular irregularly shaped object depends only on the location of centroid.
So the shape of the body is sort of encoded into the location of the centroid. If the shape of the body is bottom heavy, then the centroid is naturally going to be at a bottom location. So the shape of the body is encoded into the information of the centroid. More interestingly, it does not depend on the inclination angle. All it depends on is the depth of the centroid, and the depth of the centroid can depend, of course, on the inclination angle, but there is no explicit dependency on the inclination angle. So we can have two shapes. Okay, we can have two shapes which have a same area. They can be tilted differently, so we can have two shapes. They can have the same area, same depth of centroid, but they can have different inclinations. In fact, you can keep rotating this while keeping the centroid constant. That is, you can start rotating this object about the centroid and it would hardly change, rather not hardly change, it will not change the force acting on the object. As we have previously discussed, if we have a flat plate submerged in a fluid, there is a larger distribution of forces towards the bottom as compared to the top. This means that the point where the effective force will act on will be shifted from the centroid of the object. So now let us try to find out by how much distance does that shift occur. That is, where does the force due to all that pressure actually act. Let us again draw that schematic. In fact, let me copy it. We'll rub out the parts we don't need. So we've brought out our schematic on this particular page. Let us remove some of the extraneous parts. This particular height was h at any point, so just h. Now we want to find out what is called as the center of pressure, meaning at what point does the effective pressure act. So consider the moment about the centroid.
The moment would be along the x-axis, so it would be integral y times df. This would be equal to the effective location, that is the ycp, times the total force. So this is the general statement that we can make, that is the effective manifestation of all the moments as some sort of an equivalent moment. Now the left hand side we can write as integral y times p times dA, which is essentially equal to integral y times, so the pressure acting at any point is equal to the atmospheric pressure plus rho g h, and this times dA. So this will be equal to integral y times PA dA plus, so rho g comes out of the integral, so it will be y times h times dA. Now PA being a constant, so PA times integral y dA, but if I am taking the integral y dA about the centroid, right, if I have this red shaded area and if I integrate, if I multiply it by the moment term, that is y times dA, and integrate it over the entire area, this has to be 0, because I am taking the moment about the centroid, and for the coordinate chosen at the centroid, integral yda by definition has to be equal to 0. So this particular term vanishes, and we are left with, so effectively this particular expression effectively gives us integral rho g is out of the integral, so rho g times integral y times h dA. Now y is measured from the centroid and h is at some random point. What we want to do is ideally represent everything in terms of fixed coordinates. So let us recall that xi sine theta is equal to h. Okay, so if xi sine theta is equal to h, then we can write this particular integral as rho times g integral, so y times xi sine theta times dA. Now sine theta can come out of the integral, and thus this is equal to rho g sine theta integral of y xi dA. Moreover, we can write down the following based on this particular coordinate system, based on xi being measured from this point and y being measured from this point. Okay, so xi is equal to xi center of gravity, not the center of gravity but the xi centroid minus y. Effectively we are writing down how xi and y are related. So basically when y is equal to 0, that is we are at the centroid, xi has to be equal to the xi center of coordinate. So this total distance is the xi c, the centroid. So when y equal to 0, we are at, so xi becomes equal to xi c, and when xi is equal to 0, then the distance of this particular origin is equal to xi c, that is y becomes equal to xi c when xi equal to 0. So this is the relationship between xi and y. Let us substitute this relationship over here. This becomes rho g sine theta integral. So now we can write this entire expression in terms of y solely. So y times xi c minus y dA, this is equal to rho g sine theta integral y xi c dA minus integral y square dA. Now because xi c is a constant, xi c can come out of the integral, and this integral becomes y dA. And again with the same logic as discussed before, this particular term is 0 by definition of the centroid, and thus this becomes rho g sine theta times integral minus y square dA, and this is the second moment of area. So Ixx is equal to integral y square dA. This defines the second moment of area about the x-axis. This essentially is rho g sine theta, and the minus sign we can keep it over here, times Ixx. So now we can simplify everything furthermore and write from this particular statement. So this is now equal to this. Essentially this is what we have proved so far. So y center of pressure times the force is equal to minus rho g sine theta Ixx. This implies ycp is equal to minus rho g sine theta Ixx upon the force, and we've just proven a few moments back that the force is equal to Pa plus rho g h centroid times the area. So this gives us YCP as measured from the centroid. So we note that rho is positive, g is positive, sin theta is also going to be positive as per the sign convention. PA, rho, g, hc, a, everything is positive. Moreover, Ixx is integral y square dA, so it's a squared integral, and hence this is also positive. So this entire term is positive, and there is a negative sign outside, so YCP is always negative, meaning the center of pressure will always lie at a point lower than the location of the centroid. So this shift is equal to this entity, this shift. So this could be the YCP, or more generally this is the point CP, the center of pressure. Alright, so it's always shifting downwards, and this was sort of, we discussed it intuitively why this would happen, because the pressure is larger at a lower end. Now suppose we place this particular object at an even larger depth, that is, we increase HC. So if we increase the depth, sin theta does not change, Ixx does not change, d does not change, g does not change, rho does not change, Pa does not change, only HC increases. So the denominator increases, then YCP goes down, meaning the shift from the centroid reduces with depth. So at larger depths, the center of pressure tends towards the centroid. In the same way, we can now determine the shift of the X center of pressure from the centroid. For this purpose, let me again refer to this particular schematic. Like above, we will have X center of pressure times the force, and it should be equal to integral X times dF, and this would be equal to integral X times P dA. Now keeping in mind the same expression for pressure, it will be equal to PA plus rho G times H times dA, and this will be equal to integral X PA dA plus rho G integral X H dA. Now PA comes out of the integral, and this becomes simply X dA, and by definition of the centroid, this is equal to 0, because I repeat again, the centroid is where our coordinate system is located. We want to find out with respect to this particular centroid where the center of pressure will move. We have already found out the expression for YCP, and we are doing it for X. So now proceeding, the expression is then integral rho G X H dA, and rho G can go out of the integral. Essentially it is rho G integral X H dA. Now we can again make the following substitution for H. H becomes equal to xi sin theta dA. This becomes rho G integral X, and xi can be written as xi centroid minus y dA. This is equal to rho G integral X xi centroid dA minus rho G integral xy dA. Now xi centroid comes out of the integral, and this becomes 0 by definition of the centroid, and this effectively becomes minus rho G integral xy dA. So thus from this statement and this statement, we can write xCP is minus integral rho, okay, This is equal to integral rho g integral xy dA upon the force. So essentially this is integral xy dA divided by, so the force is equal to atmospheric pressure plus rho g h of the centroid times A. Now interestingly, we had seen that ycp is always less than 0, but it need not be the case for xcp. The center of pressure can either shift in the positive x direction or the negative x direction. That is, it can be at a certain ycp, but it can either move towards positive x or a negative x. So suppose this is the ycp, so this is center of pressure in, so the y of center of pressure. Now x center of pressure can lie anywhere on this line. It can lie in the positive x direction, that is this direction, or it can lie in the negative x direction also. It depends on the cross moment of area. So it depends on integral xy. So this can either be positive, negative, it depends on the distribution of area. Okay, if the object is symmetric, then this particular integral will become 0. Okay, let us consider an example so as to illustrate the method to find out the forces. Consider a wall like this is a brick wall, and that there is a hinged plate over here. So this hinged plate separates air on one side and seawater on the other side. Let's say that this height is approximately 3 meters. So the question is, what is the force on this particular gate due to seawater? So A, what is force on the gate? So the density of water is approximately 1000 kg per meter cube, and gravity is 9.81 meters per second square. So the force acting on the gate, so it is also given that the gate is 1 meter wide, that it is a rectangular gate, that is the cross section of the gate is something like this. So this is the cross section of the gate. It is 1 meter wide, is 1 meter into the plane, and it is given that this particular angle, so this distance is 60 centimeter and this distance is 80 centimeter. And the purpose of giving these distances is to tell us the inclination of the plate. So the force acting on the plate will be equal to the pressure at the centroid times the area. Now look, in order to find the pressure acting on the centroid, we will remove atmospheric pressure, because on this side of the gate, so on this side there is seawater, but on this side there is atmosphere. So whatever atmospheric pressure is sort of imposing on this column is negated by the atmospheric pressure acting on from the other side. So the pressure will only contain the rho g z component. So this will be rho g times the height of the centroid. So what will be the height of the centroid? That is all we need to find out. So first of all, let us get certain other parameters out of the way. The area of the plate is equal to 1 meter times, so if this is 60 and if this is 80, the length, this particular length will be square root of 0.8 square plus 0.6 square, and this is equal to 0.64 plus 0.36, which is equal to 1, so this is going to be 1. So the area is 1 meter square, and the location of the centroid will be over here, that is at the middle of the plate. So it is at a distance of half meter from this side, because we've just found out that this total length is also 1 meter. Obviously the drawing is not to scale anymore, but this distance is also going to be half meter. So what is this height? So this height is obviously going to be equal to 60 centimeter upon 2. So we have this equal to rho g times. So if this is 3 meter and if this is 60 centimeter, so this particular height will be equal to 2.4 meter. So this will be 2.4 meter plus 0.3 times the area. So this is 1000 times 9.81 times 2.7 times 1. And if we put all these numbers into our calculator, it comes out to be approximately 26.5 kilonewton. All right. Once we have calculated the force, the next part of the question is the horizontal force exerted by the wall at point A. That is, this point is called as A. So what is the force exerted by the wall on this? So that is also not that difficult to find. I will only outline how to do that. Let us draw the free body of the gate. So let this be the force acting on the plate because of the wall, and over here is the centroid, and somewhere over here is the force due to pressure, that is this particular force. This particular force is acting over here, this is acting like this, and because we're drawing the free body of this gate, there will be forces over here. So this is, let's say, reaction force X and reaction force Y. There will be no moment because it's a pin joint. Now we must perform a moment balance. So this is the centroid. We must first find out how shifted the centroid is with respect to this axis. So suppose this is YCP, then we know that this particular distance of the centroid is 0.5 meter. So the moment arm for the force because of the pressure is going to be 0.5 minus YCP. So on one hand you have 0.5 time on the one hand you have a moment which is equal to 0.5 minus YCP times FP, and this moment is clockwise and hence there will be a minus sign, and on the other hand you have a moment due to this force F, so it will be F times the momentum 1, but the sign of the angle between this and this, that is the sign of this particular angle, and that angle is easily known because the entire geometry is given. So this is equal to 0, and this calculation would first require you to calculate YCP. FP is already known, and with the help of that you will be able to calculate the force. So I've given you a brief outline. Now once we found out this particular force, how does one find out the reaction at the hinge? Let me tidy up the diagram slightly. So then how does one find out the reaction at the hinge? And the reaction of the hinge is most easily found out by doing a simple force balance on this entire member. Okay, that is the easiest part of the problem. You just have to decompose this FP into its two components in the X and Y direction. The force acting on the plate because of the wall is always in the X direction, so it will involve Rx, the component of F in the X direction and F, and Ry and the component of Fp in the Y direction. It's most simple, so it's a simple force balance. With the help of this, we are able to solve the problem in its entirety. So far we have analyzed the forces acting on flat entities, but there are many cases where the object has a certain curvature. Let us consider how to find out the hydrostatic forces on curved surfaces. Let us consider a curved surface like shown. Now, the actual shape of the object can be something much more complicated, but the cross section is something like this. It could be something very complicated, and it is submerged inside water at a certain depth. So the task is to find out what is the vertical force and the horizontal force acting on this curved member over here. In order to find this out, what we can do is a very fundamental solution. So we know the shape of the object. Let me redraw it for clarity. We know the shape of the object, and if we know the shape of the object, we know at each point what is the direction of the normal, because the gradient of the curve gives us the direction of the normal. So in elementary calculus we have formulae to find out the normal direction and the curvature of a curve. So using that, we know what the normal direction is, and we can parameterize the curve. So if this is ds, or rather let this be dA, so we know that the force or the differential force would be equal to integral p dA n cap, but it will not be n cap, it will be minus n cap, because the force due to pressure is compressive. So it will be integration of all the different forces acting on the curved surface. So this integration will not be over here, but it will be in a separate step. So this is the force acting on a differential element. Then we can integrate this over the entire surface, keeping in mind that during the integration, for each differential element, the normal will be pointing in a different direction. So the net force will be integration p dA n cap, where n cap itself is a function of the parameter. By a parameter, I am referring, of course, to, if I call this as the origin, then suppose there is some parameterization of this distance. So the normal vector depends on what location I am. So if the parameterization goes to S2 from S1, the normal vector also appropriately changes. So the normal vector will be a function of area, which is also dependent directly on the depth, because the parameterization will also change the relative depth of those points. So nothing is constant in this, and this entire integration has to be done painstakingly. However, we can not do all this complicated stuff, and instead we can apply Newton's third law to find out directly the force acting on the curved surface. Let us see how. Let me redraw the curved surface. So if the force, the horizontal force and the vertical force acting on the member are like this, we can imagine an imaginary chunk of water in the projection of the area. Let me call this as A, B, C, D. So let me draw the free body of ABCD. So the free body is something like this, and this force is the force acting on the plate because of the fluid. So by Newton's third law, there will be a force acting on the fluid because of the plate like this. Similarly, on this surface there will be atmospheric pressure because this is the free surface. On this face there will be force due to the pressure. Similarly, on this face there will be a force due to pressure. This is the outline of the object. There is no object anymore, it is just a fluid mass. But I can sort of split it at this particular point. That is, I can draw a horizontal at this point. Let this be C prime. So the force due to pressure acting on AC prime and the force due to pressure acting on BC will nullify. So the horizontal force on AC prime and BC will nullify. So the only horizontal force acting on the entire element is due to C prime D, where C prime D is actually what? It is the vertical projection of the object. So the object outline is CD, it is the vertical projection, that is C prime D. So if I am able to find out the force acting on C prime D, which is quite straightforward because C prime D is a vertical flat surface, and we know that finding out forces on vertical flat surfaces is easy. So the horizontal force, when we do the static of this entire mass of fluid, this will be equal to force acting on C prime D, which is equal to P atmosphere plus rho g h centroid times the area, where h centroid is the depth of the centroid of this area CD prime, C prime D, and the area is the area projected of the object CD onto the vertical plane. Essentially, it is the force acting on its projection. But what about the force acting in the vertical direction? Let us redraw the free body diagram. So over here we have atmospheric pressure. There is no sort of force acting on AD and BC which has a component in the vertical direction. And the last thing we need to consider is the entire mass of this fluid element, so the weight. So if we do a static balance, we have atmospheric pressure times the area, that is area of AB, plus W, and this will be equal to the vertical force. It is going to be as simple as that. And if the other side of the plate is backed by atmosphere, then even this atmospheric pressure will vanish, because this force, if we now consider the free body of the object, so this vertical force is acting over here, but there will be a force due to atmospheric pressure acting on this end also, and that will sort of cancel out. Okay, so typically the magnitude of atmospheric pressure for sufficient depths is also quite small, and in the problem it will be specified whether we need to account for the atmospheric pressure or not. Usually it is said that we should neglect atmospheric pressure. Okay, so it is quite simple. The vertical force is going to be the weight of fluid on top of the surface. And it has this particular approach, it really allows us to quickly find out the force acting on a curved surface,
because we do not need to do that complicated integral. That complicated integral involves the moving normal, parameterized area, and pressure which changes with depth. So instead of doing that complicated integral, we can simply make a control volume of the fluid subtended by the curved surface, and with the help of that we are able to find out the forces. In fact, let us do a small problem which will highlight both the approaches. Instead of doing it, instead of putting in numbers, we'll do it numerically, symbolically rather. Let us consider the surface of free water as shown, and let us consider a dam. This is the ground. So the height is given as z0. The entire width of the dam, not the width but the extent in the x direction is x0. This is the x axis and this is the y axis or the z axis now. So the question is, what is the force acting on the dam? The equation of the dam is given as z upon z0 is equal to x upon x0 whole square. So we need to find out the forces, the horizontal force and the vertical force acting on the dam. So let us first do it the parameterized way, and let us consider any area. So the width, let us say that the width of the dam into the paper is w, into the plane is w. So that's just a small detail. So now if we consider this, area, okay, so the force will act normal to the area. So this will be the direction of the pressure, and so the force at a given point df will be p dA, which is essentially p times this arc length ds times the width, but this force is now going to act in the n direction. So this is the expression for the differential force. Now we want to find out the force in the vertical direction. So what we do is we do df dot ez, and this will be equal to p ds w times n cap dot ez. Now this is the ez direction, this is the n cap direction, this is ds. So ds, so this is the n direction and this is the ez direction. So now n dot ez is the cosine of this angle, which is essentially cosine of this angle, and so if this length is ds, it will be ds cosine of theta, essentially it becomes dx. So this becomes p, so w times ds times this cos theta, so it becomes dx. Let me move this geometry somewhere over here. Alright, so this is going to be the differential force in the z direction, and we recognize that this is the force acting downwards. So I am not sort of accounting for the sign over here, but actually this n dot ez will have an automatic negative sign because n is like this, but ez is actually in this direction. So this is actually the direction of minus ez. So anyway, let's keep that sign. Let's account for it right away. So it is minus p w dx. So the force in the z direction will be integral minus p w dx, where now the pressure at this particular point will be,
So suppose this altitude, this height from the base of the dam is Z, then the pressure at this point will be rho g Z naught minus Z, because this depth will be Z naught minus Z. This is integral minus rho g Z naught minus Z times W times dx. So rho g W comes out, so it is minus rho g W. Let us take Z naught outside, so it is Z naught. Then this becomes 1 minus Z upon Z naught dx. Well, now we also recognize that Z and X do not vary independently. In fact, they are related by this equation. So Z upon Z naught is X upon X naught whole square. So we can substitute over here. So this becomes minus rho g W Z naught integral 1 minus X upon X naught whole square dx. Now x, this integration should vary from 0 to x naught, but I can divide everything by x naught and multiply by x naught. So it is like minus rho g W Z naught integral 0 to 1 minus x bar square times dx bar, and this x naught comes over here, where x bar is our new variable x upon x naught. It's very easy to see this transformation, and thus this becomes minus rho g W Z naught x naught. So this will become equal to 1 minus 1/3. You can do this calculation at your own pace, and essentially this becomes minus rho g W Z naught x naught times 2 upon 3. So this is the expression for the force in the z direction. What about the expression for the force in the x direction? It's very easy to do it if we use the same thing as a starting point. Instead of taking a dot product in the z direction, we will take a dot product in the x direction. So essentially this will become P W dz, because ds, so n dot ex, so this is ex, so n dot ex is going to be cos of this angle. Essentially this angle, if I call it as theta prime, will be this angle theta prime. So cos of theta prime will be the projection of ds on this. So let me mark it by red. Cos of theta prime will be projection of ds on this red line, and that will be dz. So it will be integral pw dz. So this is dfx, and then we can integrate it, so it will become integral pw dz, and this is essentially integral rho g z naught minus z times w times dz. Now you must be wondering why I've neglected the atmospheric pressure in all my calculations, because it is given in the problem that I have to neglect the atmospheric pressure. Hence I have not added P atmosphere on all this. Otherwise it would be P atmosphere plus rho g z naught minus z. But anyway, so Fx is essentially rho g w constant that's outside. It is z naught minus z times dz, where z varies from 0 to z naught, and this is rho g w. So let me take z naught outside, and this becomes integral 0 to z naught 1 minus z upon z naught dz. I can divide everything by z naught and multiply by z naught, and I can let z upon z naught be z bar. So then this becomes rho g w z naught. This z naught goes over here to make it a square, and if z bar is like this, then this limit becomes 0 to 1. This becomes 1 minus z bar dz bar, and this becomes rho g w z naught square. So this would be 1 minus integral z dz is z square by 2, but limit is from 0 to 1. This becomes half. I am doing it quite directly. Actually I would not have written so many steps, I would have done it directly right over here. I am just showing you the logical
train of thoughts to avoid any kind of silly mistake. So this becomes rho g w z naught square upon 2. So the force in the x direction is this, while the force in the z direction is this. Let us now see whether we can arrive at the same results with the help of the Newton's third law approach. Let us draw the dam once again. So this is z0, this is x0, and this is the origin. So this is x and this is z. So let us find out first the horizontal force. So the horizontal force is the force acting on the projection of this area. So the projection of this blue curve. So projection of this blue curve is say AB. So it is force acting on AB, and force acting on AB is what? It is simply going to be pressure on acting at the center of at the centroid times the area, and this area would be z0 multiplied by the width into the plane, and the pressure at the centroid would be rho g. The centroid would be at z0 upon 2 from the bottom point, so and from the top point. In fact, actually this PC would be the centroid from the free surface, so it would be still z0 upon 2. So this is the pressure at the centroid, and the area is z0 multiplied by width. So this simply becomes rho g w z0 square upon 2, and this is the same as what we have already obtained. What about the vertical force? The vertical force is equal to the weight of the fluid on top of the curved surface. So what is the weight of the fluid? It would be the area under the parabola minus the area of the square multiplied by the width. So let me write it down. So it will be area of the square minus area of the parabola times the width times rho into g. So area of the square is equal to x naught z naught. Area of the parabola is integral, so that integral will be integral z dx, x varying from 0 to x naught. So this is equal to, so let me multiply and divide by z naught. So integral z naught, let me multiply and divide by x also. So this becomes integral 0 to 1 z upon z naught d of x upon x naught, and this becomes z naught x naught integral 0 to 1 x upon x naught whole square d of x upon x naught. This becomes z naught x naught. So this becomes x bar cubed upon 3. So this becomes 1 by 3. So this area of square minus area of parabola is x naught z naught minus x naught z naught by 3. So this is x naught z naught minus x naught z naught upon 3 times the width into the plane. This is the volume. This is the volume of this particular area on top of the curved surface times rho g, and this is w, or rather this is rho g w z naught x naught into 2 upon 3, because this is z naught x naught times 1 minus 1/3, and this is 2/3 times z naught x naught, and in fact this is also identical to this answer with the appropriate signage, of course. So it's the weight acting on this, so it has to be a negative sign. So that much we have to be always on the lookout. So we have done the problem using both the approaches. Both of them give us an identical answer. The difference being we could do one in a very quick time, and we could obtain precise answer without doing much calculation, while in the other case we had to do a bit of calculation. I mean, for such a simple problem it's really not much of a deal, but in case the curve becomes complicated, it's not always easy to parameterize the curve and to obtain a closed form solution using an integration. But you can find out projections of surfaces rather easily and find out the net force using the Newton's third law.